What's that? No. Yeah. Yeah, maybe. It's a good idea. Biden has the slimmest of leads. He's got to hold on to leads in Nevada by 8,000 votes, less than 8,000 votes out of over 1 million. Well, there's going to be a recount there. Michigan, it's more like Biden leads by 60,000 with almost everything counted. Nevada still has 75% or 25% of all the votes. Like oh God. No. You don't want to. Today I want to talk about passive filters. So passive devices are those that don't require any additional power supply. Like active devices would be filters based on transistors or operational amplifiers. Passive filters are those made just using RLC circuits, so they don't require additional power supplies. Active filters you can typically get by with fewer components. With active filters, you can also design active filters that don't require inductors, especially audio frequencies. Inductors tend to be the size of the inductor you need tends to be pretty heavy. Inductors kind of act less like real inductors, kind of act less like ideal inductors than real capacitors act like ideal capacitors too. So, but we'll look at some passive filters can usually be constructed fairly inexpensively. We'll look at, this is a bandpass filter. We're going to look at some second order circuits today. They're all fairly similar. What will differ is what component we take the output across. So this is a source voltage, and here we'll take the voltage across the resistor. Now you can kind of hand wave your way through figuring out what this circuit does. At very low frequencies, the capacitor is an open circuit. Has a very high impedance, 1 over j omega c. So at omega, small values of omega, 1 over j omega c is large, and capacitor looks like an open. The schematic symbol reminds you what the device looks like or acts like at low frequencies. So a capacitor looks like an open. An inductor looks like a short at low frequencies. Now, high frequencies, they change roles. At very high frequencies, 1 over j omega c is small. And so capacitor looks like a short at high frequencies. But an inductor, j omega L, has very large impedance at high frequencies. So at high frequencies, the inductor is an open and the capacitor is a short. So at low frequencies, because the capacitor is an open, there's no current, there's no voltage across the resistor, the output voltage is 0. At high frequencies, because the inductor is an open, has large impedance, same thing, no current, so no output voltage. There is a frequency, since ZL is j omega L, and ZC is 1 over j omega c, or we can write that as minus j over omega c. There is a particular frequency, factor out omega L minus 1 over omega c. There is a particular frequency at which that series combination looks like a short. The two together have 0 impedance. You can solve for that. It would be where omega L is equal to 1 over omega c, or where omega, solving for this, would be 1 over the square root of LC. Now here I'm solving for a particular value, so let me put in little subscripts here. So it's not a variable anymore, it's a particular frequency at which this looks like a short circuit. That's called the resonant frequency. It's where the input impedance is just R at that resonant frequency, again, because those two in combination look like a short circuit. That's true only at that frequency. At any other frequency, impedance is going to be greater than 0. So there could be some strange things happen in resonance. Certainly, you guys probably seen you can have resonance in electrical systems, you can have resonance in mechanical systems. You guys have probably always seen that video of the Tacoma Narrows Bridge, where it's buffeted by wind at just the right frequency, and it goes into oscillation. It's because the wind gusts match the resonant frequency of the bridge until the bridge falls apart. And a simpler phenomenon is just rest your foot on the bumper of your car. And if you do it at just the right frequency, play around with it, you can get the car to jump up and down, or move up and down, with a kind of large amplitude. That would be the resonant frequency of that mechanical. You've got springs and dampers in there with shock absorbers of that particular resonant system. Resonant systems are useful, as at resonance is where we'll actually have a maximum voltage, because at any other frequency, the voltage would be less than it would at resonance. At resonance, because this is a short, VR is equal to Vs. At any other frequency, this is no longer 0 impedance, and you've got a voltage divider effect. You can, I'm not going to go through the derivation because I just want to show what the response of this looks like. It is a voltage divider. And you can do it with J omega or S. And it's a pretty quick derivation to show that this is the transfer function. And just substitute SL for the impedance, 1 over SC for the impedance of the capacitor, and solve for the transfer function. The frequency response would be, and then 1 J omega squared is going to be minus omega squared, that's real, and then plus J omega RC. So this is the frequency response, okay, substituting in J omega for S. And then the magnitude response, the magnitude of the numerator is entirely imaginary, so it lies along the imaginary axis. So that would have a magnitude of omega RC. The denominator is complex, but the magnitude of the denominator would be square root of the sum of the squares of the real and imaginary parts. At the resonant frequency, you can kind of see it here. At the resonant frequency, when omega 0 is equal to 1 over the square root of LC, then this is going to be 1. You have 1 minus 1 here, so that's going to be 0. You have omega RC over the square root of omega RC squared. Or at the resonant frequency, the magnitude response is 1. And that goes along with the output being equal to the input. The phase response would be phase angle of the numerator, which is entirely imaginary. So that's 90 degrees minus the inverse tangent of the imaginary part over the real part. So these are the general formulas. Calculator or any sort of graphing software, given an RLC value, you can plot these. We can learn a lot just from the equations, though. Here. If we plot that response, the magnitude response, it's going to look like this. Omega. It's got this frequency called the resonant frequency where the response is maximum. And again, at very high frequencies, we know the output is 0. And at very low frequencies, the output is 0. It's going to look something like this. And we can talk about so here at this peak, in this case, that's where this is equal to 1. We talk about the bandwidth as being where the response is down by a factor of 1 over square root of 2. Square root of 2 is 1.414. 1 over square root of 2 is 0.707. You work enough with those numbers, they kind of stick in your head. So that's we call these the lower and upper cutoff frequencies. That the difference between these, I mean, again, it doesn't really have a well-defined bandwidth. So we take this 1 over square root of 2 point, the frequencies at which the response is down 1 over square root of 2, to be, we define that to be the width of this function. That turns out to be where the power is down by 1/2 of the peak power. Okay, the amplitude is down by a factor of 1/√2. The power is proportional to amplitude squared. So the output power would be down by a factor of 1/2 from the peak power. So you hear those terms called the 1/√2 is 3 dB, so 3 dB frequencies, corner frequencies, cutoff frequencies, half power frequencies, all those terms are used. We've already found you don't want to go through this analysis every time, right? So let's say you want a bandpass filter, you use these equations to help you pick the L, C, and R values that you need, right? Typically you have, let's say you need an omega-0 of 10,000 radians per second. You might pick a capacitor of 1 microfarad and then use this formula to calculate the corresponding value of L. We usually allow one kind of free circuit parameter. So pick a capacitor. You know what resonant frequency you want. You know what frequencies you want to pass through, and then use this formula then to calculate the corresponding inductor. Or maybe you go in and pull an inductor off the shelf that's 20 millihenries. Again, you could use this formula to calculate the capacitance that you need. The corner frequencies, you can solve for them in terms of I think he has this derivation in the book. This is the lower cutoff frequency, the upper cutoff frequency, is similar, except it has a plus sign here. So these would be kind of nasty to work with if you work with omega C1 directly, but it is true that the geometric mean of the cutoff frequencies is equal to the resonant frequency. It looks as if omega-0 is halfway between these. The arithmetic mean, you add them together and divide by 2. It's not quite true. It's actually the geometric mean of those two cutoff frequencies. But the other formula that's really nice is the difference between these. Okay, that's the bandwidth, omega C2 minus omega C1. Fortunately, this whole square root term cancels, and the bandwidth is simply, it will just be R over L. Yeah. So here are your nice kind of design formulas. You typically would specify the resonant frequency and then the bandwidth of the filter that you want. So, and you might pick an L, given the resonant frequency, you can use this to find the C. And then from that L and the bandwidth, you can use this to find the R that you need to get the bandwidth and the resonant frequency you want. There's another design parameter called the quality of the filter. It's unitless. It's actually the resonant frequency divided by the bandwidth. Since both those are in radians per second. Bandwidth is not always in radians per second. If we converted this to hertz, then we could express the bandwidth in hertz. But the quality would be the same. But if you stick our formulas in for, we can also work with the quality. And it's 1 over R times the square root of L over C would be the quality of the filter. And it is true for high Q circuits. So a high Q circuit would mean that you've got one, for the same resonant frequency, a high Q circuit is going to have a smaller bandwidth. same omega 0. As Q will go up as the bandwidth decreases. So high Q or high quality circuits would have a sharper bandwidth. This would be a higher Q circuit that would have a narrower bandwidth than the lower Q circuit. That would be one with even a lower Q. There's one more approximation that is useful for high Q circuits. And in this textbook, he says high Q is for Q greater than 10. Some say greater than 5. It's just a rule of thumb. But for high Q circuits, omega 0 is approximately, and this is actually a pretty good approximation, is approximately the arithmetic mean of omega C1 and omega C2. Sorry, I got too low on the board. That's omega 0 is approximately 1/2 the quantity omega C1 plus omega C2. So that's a little easier to work with than this geometric. So he has coming on now. That's why this one was unplugged, because the same remote stupidly controls both of them. We have the backup remote. So this is showing this bandpass filter for a Q of 2, a Q of 5, saying medium selectivity, and then a Q of 20, and then the corresponding bandwidths here. The bandwidths get smaller and smaller. The bandwidths get smaller as the Q gets larger. Now, you don't always want a high Q circuit. If you're trying to pass maybe just a single tone, a single frequency, you might want a high Q circuit. But depending on the Fourier transform of the signal that you're dealing with and the signal content, you typically want to try and pass all your signal while filtering out anything else. I'll leave that up there. There's some other pictures I want to show. You can actually, we can rewrite the response in terms of omega 0 and Q, where H of S then is S over omega 0 Q over S over omega 0 squared plus S over omega 0 Q plus 1. Okay, so that was a second order bandpass filter. Second order because in this particular case, the denominator's second order. Okay? If it's a ratio of first order terms, or if the highest order, either the numerator or denominator is first order, then it's a first order filter. These RLC circuits will be second order filters. For a high pass filter, we actually just take our output across the inductor. It's the same series combination, but we take our output across the inductor instead of the resistor. And again, kind of the hand-waving argument would be, at low frequencies, the inductor is a short. The voltage across the short is 0. So at low frequencies, our output voltage is 0. At high frequencies, this is a short, but this has large impedance. Okay, the inductor would be like an open. So there would be no current, and the output voltage would be equal to the input voltage. So the output's 0 at low frequencies, and it's equal to the input at high frequencies. You can mentally picture that. That's a high-pass filter. You might expect, and you'd be right, if we actually swap the L and the C, you'd have a low-pass filter. The response here is S squared LC over S squared LC plus SRC plus 1. The other thing you'll note about all these filters, second order filters we talk about, is the denominator is the same in each case. And that you can figure that out from voltage division, because it's always the impedance of what we're taking our output over the sum. So the sum is, because this series circuit that we're using, the sum is the same in all the cases that we'll look at. So the denominator is the same. You know, the other way to figure out what's going on with this is take a look at, as either omega goes to 0 or S goes to 0 here. As S goes to 0, this is 0. But as S becomes infinitely large, this S squared term dominates the denominator. And you have S squared LC over S squared LC over 1. And the limit is S becomes infinitely large. So it's 0 at small values of S, 1 at large values. And this is a little tough to figure out. You can figure out what's going on at low and high frequencies. At low frequencies, it's 0 because the S in the numerator. At high frequencies, you're going to have a 1 over S dependence, right? This term would dominate. You have a 1 over S behavior, but that goes to 0 as S becomes infinitely large. So the question is, what happens in the middle somewhere? And that's where the resonant frequency comes into play. In terms of the frequency response, it's minus omega squared LC, again, 1 minus omega squared LC plus j omega RC. And you can rewrite this as, in terms of omega 0 Q as S over omega 0 squared, S over omega 0 squared plus S over omega 0 cubed plus 1. Then where omega 0 is still 1 over square root of LC, and Q is 1 over R square root of L over C as before. Now, if you here's a plot of that high pass response, and omega 0 is approximately the corner frequency of this high pass filter. It looks a little odd to have this. Actually, if you make the Q lower, you don't get this peak at the corner. It looks a little odd to have that peak actually, and the peak gets larger as Q increases. Right? Really, what we're after now is talking about this high pass filter. So notice here with these second order filters, the slope here is 40 dB per decade. on this side because it falls off at low frequencies. It falls off as S squared or omega squared. At low frequencies, the 1 would dominate. Whereas a first order high pass would decrease at a slower rate, actually at 20 dB per decade instead of 40 dB per decade. So what about this bump here? Usually these second order filters are components of higher order filters. So we can get really nice responses with maybe 4th order, 6th order, 8th order filters. But we know, if I have an 8th order numerator denominator here, I can factor that always into 1st order and 2nd order terms. I know if the coefficients are real, that the poles and zeros will either be real or they will occur in complex conjugate pairs. The complex conjugate pair terms become 2nd order terms. So any higher order filter I can write as a product of 1st order terms and 2nd order terms. That's a consequence of using real coefficients that are always positive here. Low pass filter. I think I mentioned this one already. We just have to swap the inductor and the capacitor. C, BS, R, L, C. I'm just going to give you the it's the same denominator. What's different in every case is the numerator. Again, as you take the limit as s goes to 0 here, this approaches 1. Take the limit as s becomes infinitely large, then it's 1 over s squared or approaches 0. So this would be a low pass. You can make that argument, thinking about the components and how they act. At low at low frequencies, my capacitor is an open, so there's no current. My inductor is a short, and the output would be equal to the input. But at high frequencies, I've got 2 things going on. I've got the inductor that's blocking the current, and this thing's acting like a short. And so at high frequencies, the output voltage would be 0. And you can get that from this expression. The frequency response is 1 over 1 minus omega squared LC plus j omega RC. So that's the same. The resonant frequency is 1 over square root of LC, and the Q is the same.
Excuse me.
Yeah.
That Q, are you multiplying the denominator by the root of L over C, or?
No, it's in the numerator.
Right.
It's 1 over R times. Yeah. So this is the corresponding low pass response with a cutoff at omega 0. Kind of looks like the mirror image of the high pass response. Again, on the edge, the response rolls off, and this is our Bode plot. So this is in dB. But if you'll notice here, as we go from omega 0 to 10 omega 0, there's a change of 40 dB, whereas with our first order circuits, we were seeing a change of 20 dB. I'll go from here to, so first order circuit would be like that. The last one, and I'll just show you this one. This is the band reject response. Actually, I guess it doesn't have the circuit there, so I'll show you the circuit. You might reason out what the circuit would be here. We know at resonance, this has 0 impedance. So that's what I'm interested in with a band reject filter, RLC, band reject filter, or sometimes called a band stop filter. It's S squared LC plus 1 over the same denominator. You can show that the band reject filter is actually 1 minus the bandpass transfer function. The same would actually be true for the frequency response as well. Right, so this is showing the band reject filter response as a function, as a Bode plot. You know, for a higher Q, you get a narrower rejection region. For a broader, a lower Q, you get a wider rejection region. So the purpose of this filter would be to eliminate an interference at a frequency, as opposed with a bandpass filter, we're interested in passing through a particular signal. And this figure is just showing a comparison of a simple RC low pass and a second order RLC low pass. And how you get the steeper roll off with the second order circuit, 40 dB per decade versus the 20 dB per decade. And the disadvantage is you've got an extra component, so there's additional costs there. And again, at audio frequencies, inductors tend to be large, okay, and heavy. So generally try to avoid them as at radio frequencies, inductors can be pretty small, just a few loops of wire. But at audio frequencies, the inductors we work with that get any appreciable impedance, you know, have to be fairly large compared to the capacitances. It's difficult to get an inductor on a printed circuit board as well. So there's trade-offs. Certainly, if this is good enough, it's cheap enough, depending on the application, this first order filter may be sufficient. We do have a filter design course, an elective course, where we actually look at designing active filters, higher order filters, you know, that have very sharp roll-off, bandpass filters, reject filters. This is just a table from the textbook. It's just got a summary of all of these equations. I've shown you the series response. Actually, for the bandpass filter, this is the one we started with. You can also do these. There's an equivalent kind of parallel layout for these. This is with being fed by a current. But at resonance now, the parallel combination, and you can verify this, it's the product over the sum, right? So at resonance, if the sum is 0, in parallel, you're going to have an infinite impedance. So at resonance, this parallel combination looks like an infinite impedance, where in series, it looks like a short circuit. And the other thing is, there's some strange things that happen at resonance, right? I mean, we said at resonance, this voltage, this band reject filter at resonance is 0. That doesn't mean the voltage across the inductor is 0, though. It could be equal and opposite. As a matter of fact, because the currents are the same, right? But the inductive impedance is a J. So let's say VL is I times J omega L. The voltage across the capacitor is I times minus J omega C. So the voltage here is going to be 90 degrees ahead of the current because we're multiplying by J. The voltage across the capacitor is going to be 90 degrees behind the current because we're multiplying by minus J. So they'll be 180 degrees out of phase. That's what's going on. They're equal but opposite. So they're not individually 0, but they sum to 0. So it's a strange, there is current flowing, but it is a strange phenomenon.
The omega, it's supposed to be numeric.
Yes, thank you. All right, any questions? Let's go home. Not to my house, go to your own house.
We're